Okay, this is good. So we're going to have a nice keynote speaker, Timos Kipouros, did I say that correctly? On visual analytics for the direct support of value assessment. I'm not going to say scientific things about Timos because you will hear the science from Timos himself, which is going to be much more interesting than me trying to say anything. But I would tell the story of how Timos and I met, just because I think it's kind of fun. So there used to be a very gifted student here by the name of Zhao Gang, and I don't even think you know the whole story. Zhao Gang was, he finished, but he, at the time, in 2011, was a PhD candidate in data visualization, studying high-dimensional data. And he did some really nice work on parallel coordinates, which he actually presented at the Viz conference in front of a very large audience. And so we published that paper, and I believe, I can't be 100% sure, but Alfred Inselberg was one of the reviewers. He might not have been a reviewer, but he definitely read the paper, and he read it much earlier than a normal person would do. And he wrote to us. He wrote to me and Zhao Gang saying, "Hey, I really like your parallel coordinates paper. That's nice." And for me, that was a special moment, getting an email from Alfred Inselberg, who's one of my Viz heroes. He's definitely one of my Viz heroes. In fact, I printed out the email, which I only do once every 5 years. So I print out the email. And I think it's still hanging in my office. I think you can still. It was hanging in my office for many years. And then he wrote back a few weeks later saying, "I'm coming to the UK," because he's based in Israel. He said, "I'm coming to the UK. Maybe we can meet up." I had already met him, by the way, before that. And I was like, "Really? You're coming to the UK? How is that possible? Does not compute." And I was like, "Who is this person that invited Alfred Inselberg to the UK?" And it was Timos. He said, "Yeah, call Timos. I'm going to be at Cambridge University, and I'm going to give a talk there, and you guys should come to Cambridge and to the talk and visit, and we can all chat." And then we met. I got to meet Timos. So that was a really fun meeting. I still remember that meeting. And Timos and I have been just bumping into each other kind of regularly ever since then at various engineering and simulation and visualization-ish events. And every time I see Timos, I say, "Oh, you should give a talk at Swansea University." And it dragged on for so many years. I was embarrassed. I say, "Oh, I still have it on my to-do list, Timos, to invite you to Swansea University to give a talk." And it was getting embarrassing for me because I was saying it many, many times over many years. So today I finally get to check that box and have Timos give a special talk, a special keynote at CGVC 2018. And also, I suggest that after this excellent keynote talk, we do a group photo, which is also a little bit unusual, on the steps of the Digital Technium. So it's actually just outside here. You can notice some nice steps. It's a nice staircase. So after that keynote talk, I suggest we go do a group photo, and then we'll have some lunch. Sound good? Any questions? Comments or anything like that before Timos gets started? Good? Good? Okay. Timos.
Thank you very much, Bob. So indeed, thank you very much for the invitation. Yeah, it's loading. And giving the opportunity to visit Swansea for the first time. And I always wanted to visit, so I ticked my box as well. Then Then I have a similar story as Bob's with Alfred. So then I've done my first paper using power coordinates to analyze some of my data. And then he came back to me on the same fashion by email saying, well, I like this paper, let's meet. And then at the time, that was back in 2008, I think, and then in 2009 he organized kind of tutorials in Peking University in Beijing. So then he invited me to attend the course and then give a talk also. And then that was, I couldn't miss the opportunity, and that was the first time to meet him. Now, it happens to talk a bit more about Alfred, but then my whole talk is about power coordinates anyway, so let's give him a couple of more minutes. The very interesting part of Alfred to me was like he also speaks my language. My native language is Greek, which was really, really surprising. So when I first go to meet him, hello professor, my name is Timos, comes back in Greek, and I was really surprised. So the guy is full of surprises all the time. If you haven't had the chance to meet him, it's an experience. So, as you have gathered, perhaps my background is in engineering. So I'm placed in the Engineering Design Center at Cambridge. So this is how our lab looks like. So we're located up here. This is the loft where it started. I moved there 16 years ago. Now we moved here in a bigger area. Not sure if you can see the colors correct, but anyway. So we do a lot of engineering design, of course. That's why it's an Engineering Design Center. But we do computational design. So we run a lot of models, we do simulations, we produce a lot of data and numbers, and then we need to make sense out of this information in order to support the decision making and build engineering products. Now, we have a big portfolio of different collaborators. My specialization is in aerodynamics, so I work primarily with aerospace. So these guys, Airbus and Rolls-Royce and GKN primarily are major partners in many projects. So then, what you will see next relate to this type of application. So we'll build aircraft components or engine components, and then we will try to do the analysis using visualization techniques and visual analytics, and then make sense out of this. I work in two different groups. One is the computational design group, led by Jeff Parks, and also in the change management group, where we model and simulate changes in engineering products, and that is led by Professor John Clarkson. Now, why we do all of that and why we like to have computational design approaches in aerospace is because it's a very challenging field. It comes with many conflicting requirements. It's not only the aerodynamics, it's of course the structures, it's the noise, it's elasticity, materials. Now the tendency is to move more towards electrical aircraft, so we have additional thermal issues. So it's a very complex environment to work. So then you need to not only capture these different kind of requirements, but then you need to communicate them as well. So that makes it really challenging and attractive at the same time, of course. So we are favoring in computational design approaches, and the reason for that is because once you build a model, then you can start exercising the model, and then you can do this very quickly, at least much, much quicker than if you did this manually, as happened like many years ago, many decades ago. Now, of course, you do that in the models. Models just simulate the reality, so they are not that accurate, but at least they can tell something. So this is something is what we try to extract when we exercise models. We know they are not accurate, they are not absolutely correct, but then it allows us to explore design spaces very efficiently and much larger design spaces than normally we do. Now, perhaps a drawback is it difficult to do? Yeah, perhaps that statement is more true a few years back. Now there are many commercial platforms that offer the opportunity to set up a computational experiment and do a design study. But then still there is a long way to go in order to make sense out of these studies. So I won't bombard you too much with engineering information, but then I would like to set up the scene in order to appreciate how visualization is important for that. Okay? So I won't stay too much in detail when I show pictures like this, for example, where that is a workflow for performing computational design studies. But then, if you like to keep four key characteristics of that, one is to manage the geometry. Imagine you have some sort of component, a wing or a component of an engine or something, and then you try to change the shape somehow. There are a number of ways, perhaps you know more than I do, freeform deformation, NURBS, so similar type of approaches. So we manipulate the geometry. Then somehow you need to evaluate the new geometry, you need to assess it. So of course you do some sort of computational fluid dynamics, finite element analysis, again heavy computational models. Once you extract your flow properties, then you can feed this into your intelligent and favorite optimization routine, and that decides what is the next candidate configuration to assess, and that loop goes for a while. Well, it goes until you run out of time, really. That's typically what happens in the real world. And then here I have another box which says whether to use a meta model or not. That is, once you start populating information, of course, then you can build a surrogate model, a response surface of that, and then you can take prediction rather than running the expensive CFD. The CFD can take a few minutes, a few hours, or even there are cases that such models may take days. So it's really expensive. Now, how that fits in the overall picture when we do design, and by no means that's not detailed, it's more kind of a cartoon way to show or to explain perhaps the process of engineering design. So you start with a process description, you need to formulate your problem in order to enable research and optimization, and this is where this computational design cycle fits. Now, once you do that, and you might have multiple optimizations and searches running in parallel, then you synthesize all the information here, and then you need to perform decision making. So you need to make sense out of this, and then you take decisions what to do next. Now, you come with a set of solutions, you validate them, and then you might need to review the problem, the formulation, and so on. So this loop goes for a while. So I've highlighted these two boxes because this is where we will focus today. And then this is where actually is the visualization really, really important. So perhaps with the next couple of slides you might be very familiar, but then it's a good way, I think, to show why visualization is that important and visualize information. Yeah, I can see smiles here. So I picked up this data set from the web. So imagine we have 4 different experiments. We measured 2 properties. We did our experiments, we record the values. One way to visualize them, of course, is a table, like that. But we cannot quite tell what happens with those numbers. If we do some statistical analysis, then you can extract the statistical properties. And then for all of those 4 experiments, the statistical properties are almost identical or very close. So someone might extract some conclusion based on this type of analysis, which is fair. However, if we visualize this for different experiments, then they will look like this. And of course, they tell a different story. It's not quite exactly the same. Of course, this data might be man-made, but it might happen in a real situation, like you might have discrepancies like that when you do experiments. So then really visualizing information is very, very important. So that is one thing to keep in mind. And then the other thing to keep in mind is in this simple example, we only had 2 different properties to visualize and process. You might also be very familiar with this quiz question. Which of the 2 blue lines is larger? And many of you might say it's the same, or some others might say these look a bit longer. But actually they are exactly the same. So it's the perspective, how you look at the data. Okay? So that is also important. What else is important in engineering is the context of the information. Because aircraft is a very complex machine, say. It is comprised of many different elements and many different engineering disciplines. So someone who specializes in aerodynamics, when you talk about an aircraft, might have something like that in mind. Someone specializes in engines might have this figure in mind. But I don't know how many aircraft you've seen that look like that. We need something that combines all of them together. Now, communication from this area to that area is not always easy. But then if we use the information and visualizing the information, then we can bridge this gap in a way. So then that is one of the main topics, if you like, of my talk. Now let's go through an example and then see how is that possible and how is that useful. Again, don't stay too much on the details, but I'll explain briefly. Now that is an engine that That's a cross-section of that. Then we focus on this particular component, we call it compressor. In a very brief way, how that works, it sucks air in, compress the air. The reason for that is we like to fit as much air as possible into the combustion chamber. Combustion follows right here. And then we produce a lot of energy with extremely high temperature hot gases. We let them expand from there, and then there is propulsion or thrust produced, and then keeps the aircraft flying. That's the purpose of the engine. At least one of the purposes, of the major purposes. Now, you see here, if you can see actually, there's a number of rows, we call those, and then one of these comes out here, and that is a blade. So we have many of those blades fit into here. Actually, you can see a lot of more blades, but then we focus on this particular compressor. Now, that is a CFD simulation, and what you see here is the velocity. And how to assess whether the aerodynamic performance of that is good or not. Then we have a number of criteria or objectives in the context of an optimization problem. So we have 4 different objective functions that we have identified. Now, when we do real-world optimization, we shouldn't neglect the constraints, because if you miss some of the constraints actually give practicality of your optimization study. If you miss some of the constraints, say the mass flow means how much air goes through this particular component. So if you neglect that, and then you do your optimization, you come up with a design that has different requirement of the mass flow, well, it doesn't fit back to the engine, so pretty much you waste your efforts. So identifying this type of constraints is really critical. Now, we have the list here. Now what it is to do is to model these 3D changes of the geometry. So we pick up one particular technique, partial differential equations. It comes with 26 parameters to modify, and then we consider those objective functions in order to perform the design, the optimization. We've done this in terms. That means we consider that objective first, subject to the same set of constraints always. So single objective approach, bi-objective approach, 3 objective and 4 objective. When we did the single objective, we found this design. That was a reference design. That is what you find when you do the single objective optimization, considering that objective function. And then we tested that experimentally, and then we validated the predicted improvements from this outcome. When we approached the problem from a bi-objective perspective, we came up with a Pareto front here. What we see here is the history, and then the black dots is the Pareto front. And then we pick up 2 extremes as an indication of what sort of shapes these dots represent. And you can tell actually they are very different. And that raises questions. When we did the 3 objective approach, the target is to minimize all, so we're focusing down here. What you see here, the black dots are in 3D Cartesian, the RGB colors are the projections. Again, picking up 3 extreme designs. Again, they resemble more in the bi-objective case, not quite to the validated, experimentally validated single objective outcome. And that still raises questions. When we consider all the 4 critical criteria to assess aerodynamics, pick up again. So the target is again down here, the same corner. Now we have the color contour for the 4th objective. So we're looking for dots, green dots around this area down here. Picking up some designs, then that one might remind you the single objective design. So if I show you some other pictures, these are highly 3-dimensional geometries. Now, the point is to understand actually what makes this design to behave better than the reference geometry where we started. And that was a real geometry, by the way. And then with that understanding, then you can, of course, have more informative decisions to make. And that was only doing aerodynamics. We neglected here structural integrity, for example, although we only had one manufacturing constraint. So then, not only to understand why these designs behave better, we also need to communicate these methods with other domain experts, with structures, for example. And then you need to come to a common decision. So the methods, okay, it's to include all of the properties that are actually critical to assess performance of various components. Now, the answer to that is, of course, visualizing this information. So what do we need to visualize? It's not only the Pareto fronts, or the optimum designs in the sense of objective functions, but also the design parameter space, the 26 properties that we identified to change the 3D geometry. So that will make up to 30 dimensions, and then of course we need to find a way to visualize. But Alfred did this for us, like many years ago. So then we just picked up his technique to do that. Now, are you all familiar with parallel coordinates? Do you know how it works? I can see you know that. Okay. However, still, although as a concept is very simple, there are some things that are interesting and not actually many people grasp. So, that is a Cartesian xy, as we are all very, very familiar, even from school. This is a parallel coordinates. So what that means is if I put a dot here, say x2 is 0, x1 is 1, then what you have is x1 is 1, x2 is 0, and then you have one line. And then you put dots, and then you have lines. Okay? Now, what is interesting is, if, for example, you have certain relationship between two properties, then you have a certain behavior or pattern in parallel coordinates. So, for example, if you have some sort of a positive correlation between two properties, then what you see is those lines are parallel. So if you see something like that in a complex parallel coordinates plot, as you will see next in a few minutes, then you know those two properties are actually in harmony. So you don't need to consider both, just one, the other will follow. If those properties have negative correlation, then what you see, the lines rotate, and then you have a rotational point here. So then you can tell now that you have a negative correlation between these two properties. So again, that is a useful information just by looking at the parallel coordinates plot. What is more is you might have shapes. So if you try now to mimic a circle, more or less, what is interesting to me is, if of course I had more points here, then you will see here some sort of a curve, and that again will tell you have some sort of shape. Okay, so either a circle, an ellipsis, and so on. So this is something like we need to keep in mind, because the parallel coordinates plots, again, as you will see in the next couple of minutes, it's quite confusing. But then, of course, there is things you can tell just by looking at it. Now, if I come back to my slides, or actually, I can show you this interactively. Pick up this first data set. Now, what is the result from this problem that I introduced? 26 parameters, the axis up to 26, and then that is the data set with 3 objective functions. We have 3 criteria. And then we need to make sense out of this picture. Well, actually, we like to identify patterns here. Because if you identify patterns, then that means there is a particular trend within your design space for certain behavior in terms of your criteria, and that gives confidence to make a decision. Here I only represent the designs that are that comprise the Pareto front, so these are only the optimum designs, and there are 54. The experiment was with 2,500 configurations. Now, this software is under development, and I picked up the latest version a couple of days ago, and I can see some noise in my data. And you can tell that, for example, for this one, X5, the limits are 0.048 and 0.048, so that's effectively the same point. But for some reason, they look like this. My point is, if values of certain dimension is constant, is fixed, as it is that one, although it looks like the ranges are the same because I'm familiar with the data set, then it doesn't add any value to keep it in the picture in order to identify the patterns because it's a fixed value. Now, this value was different from the reference value, but it has this particular fixed numerical value here because it represents the optimality level subject to these constraints. Okay. But in terms of my exploration and discovery of patterns here, it doesn't offer any value. So then I will eliminate this as well as some others. Now, always when you project, the behavior is not as you want. But okay, let me see. So X3 should go, X4 should go, X5 goes, X6 goes, and there are a couple of more down here, so it's X19, X21, X22, I think. Okay, So now we have this picture, and then we need to identify patterns here. How to do that? Well, because these are data coming from a computational design study, then the approach is to consider the criteria. The criteria are the objective functions, of course. So if I bring up one of the projections of the 3D Pareto front in terms of criteria 1 and criteria 3, then that will look like this. Now, the pattern, in other way, you can call it a cluster, and then perhaps this group of designs here might be a cluster, and then I would like to explore that if that is the case. So then we'll select these designs, and then I would like to see how that looks like. Back to my power coordinates. If I clean it a bit, hide the points, that looks like that. And to me, that is a pattern. That is a cluster. There is some variability, but that is acceptable. Okay. Of course, that always depends on the sensitivity of the parameter. But given that the objective functions are very similar, so this sensitivity is not that influential. So then that is one pattern which I keep in mind. If I then move on, I would like to explore a bit more. Now I would like to bring all of the points. With another scatter plot. So I've explored this group of solutions, and of course the next one to explore will be this one. So let's try to do it. Now, that's almost the case. So if I clear this, because there is some particular trend, but then for some particular parameter, then the difference is quite significant. It's almost taking the two extremes. Now, one message here is to perform or to take decisions based on the objective functions only, on your criteria, might bring situations like this. Because from this group of solutions, 23 solutions, you could pick up any, because in terms of the objective functions, it's pretty much the same, so any will do. However, you can see they are quite different here. So they might reflect to different geometries, of course. So if I wanted to clean this, there you go. So that looks more like a pattern to me. Now, if I wanted to compare the two, that should look like this. So these are the two distinct patterns that I identified. Now, there are common characteristics, they share common characteristics, but then there are differences as well. And that's fine. And that is 30 out of 54, so that is more than 50% of the optimum designs. So it means I identified two sets of solutions effectively out of the 54. So that makes a decision much easier, because you have to choose one of the 54, now you have to choose one between the two. And remember that it's only aerodynamics, so you even need to communicate this finding with the other domain experts. So if I come back to my slides then, that's in pictures exactly the same analysis. Now if you visualize the geometries, there are differences in this particular area, that is the lean, as they call it. So that one is more aggressive than that, and then the structural guy says, okay, that will never make it, so discard it and then go for that. For the aerodynamicists, it doesn't make any difference, because following the Pareto optimality definition, all of them are equally optimal. So then, as aerodynamicists, somehow we go for that, and then the structures guy can actually do his job better. And then, remember earlier in that kind of cartoon shape of describing the design process, I'd say that it's iterative process. Every iteration, it takes a lot of time, it is very expensive. So if you eliminate this number of iterations, that is really worthy for the company. So doing this type of analysis and communication, of course, we can appreciate what is the impact when you do engineering design. Of course, they share common characteristics as well. From a different perspective, they look very, very similar, almost identical. Now, remember here I only show the optimum configurations. But remember, we've done a few thousands of evaluations, so that is still a lot of information available. And if I wanted to make more sense out of this computational study, of this effort that I put, then you can actually visualize the whole history of data. And what we see here is a few thousands of designs, all the history. And then what I have selected here is what makes a design infeasible and what makes it feasible. Infeasible is if the shape is too aggressive and then the flow detaches. That is a very bad design, it's infeasible. You never want to build that. Now, the green pattern is the infeasible designs, the cyan color pattern is the feasible design. And then you can see again here they share common characteristics, but they have distinct differences in this area and that area. And that is actually a very interesting point, because with that you can extract the information to make you understand what makes a design to be feasible and being infeasible. And then if we show those geometries, that was this particular characteristic, which is the thickness at that particular location of the blade. I wanted to go a bit more kind of physical explanation. Is in one case the flow detaches, of course, but there's not enough momentum to make it to reattach, whereas in the other case it does work. But then again, that is an interesting understanding and very useful, very valuable understanding in that domain. It will continue along the similar fashion, but then we try to deal with a larger problem. So now remember earlier we considered only one of these blades, now we consider all of them together. So we consider the whole compressor core. Again, we identify now different objectives in order to assess the whole component, the whole subsystem of the engine. Of course, the constraints, and now we have 45 design parameters, which are physical quantities, and we have 2 objective functions. Again, I'd like to show you that as a demonstration. That will look something like this. Now we have 45 parameters and 2 criteria to consider, that is 47 dimensions. One aspect of course here is to appreciate I could have 100. If my screen was big enough, then I wouldn't have a problem to visualize them. Okay? So that is another really powerful thing about this power coordinates approach to visualize the data. Again, we need to make sense out of this mess. That's another thing, because if you present these pictures to people, and then if they're not familiar, then they just laugh sometimes. Okay? And then I can feel, I can understand. And then, of course, is the interactivity, which is really important, that makes this picture really useful. So the approach is the same. I will use my 2 assessment criteria in order to try to explore the data. So that is effectively the Pareto front. And then again, here I only visualize the optimal configurations, 724 in this example. Now, one aspect as a designer is, although the Pareto front comes with 2 extremes, we never go for those. Because that means you heavily optimize in terms of one aspect. In this case, this particular extreme is heavily optimized in this particular criteria, whereas that extreme optimizes that one. And that makes the design often very sensitive to changes. Because for these simulations, we consider certain operating conditions, but then those conditions, of course, in real life, they're never fixed. They deviate. So the interesting area of the Pareto front, typically, is the compromise area. Is the area that balances well all the criteria. Now, in this particular trade-off, the compromise area, near to the compromise area, there's a big gap, there's a discontinuity. And that raises, that's an interesting feature, and that raises questions. And then we would like to explore it and then see what does this mean, or what causes this discontinuity. So if I choose this area, which I think I did, then the picture looks like that. If I clean it, now it looks like there are 2 different patterns in a way. One is down there, one is up there. And to explore that, I'd like to make the selection of one of the 2. And indeed, that looks like a pattern. Now, if I go back to my scatter plot, that reflects one side of the discontinuity. Okay? Now, if I cancel that, this is one pattern which is very interesting. So there's particular trend. The other is different pattern, but they are again so close to the criteria with some discontinuity. And then again, there are extreme values for this particular and some other actually parameters as well. And that raises again the questions to the domain expert. And then they can tell you if that was a number of blades, for example. Again, you never go above 25 if that was the case in one of the two. So that gives you the feeling what is the right decision to make around this discontinuity. And of course, the understanding again how it is. So that is again the pictures of the same analysis that I did. Now, that takes us, remember here, I've done the experiment, produced the data, I did the analysis. Of course, that raises a question and say, okay, why you don't do that during the design process? As the optimization process evolves, you identify these kind of features, then you don't let your optimizer go to the areas, to the regions that you are not interested in anymore. Okay? So then, we would like to introduce the human back to the computational design loop. Because these computational design studies are automated processes, and that's very good, that's brilliant. But then, if we bring the human back to the loop, and then you allow some sort of interactivity with the process, then of course you can benefit even more. So what you see in this picture is this automated cycle that is more visual than the previous block diagram that I presented. So again, you have the geometry manipulation, you have the simulation, your optimization, and the post-processing, and your HPC working hard in the background. Now, that is the process. What other feature I've highlighted here is the flow of information as well, which is really, really important. And you can appreciate that the more you go through the cycle, the more information you produce, the more information you need to manage and post-process. So one way to post-process, of course, is this power coordinates analysis that I just demonstrated. And we like to do this interactively as that one evolves. So effectively what you do is you take this cold information, you bend it into hot information, and then you feed it into your computational design loop. So then we move towards this direction. And then we develop prototype platforms to facilitate this. So what you see here is another example, just a simple airfoil for demonstration purposes. So that problem was modeled with 8 properties to change, modify the geometry, and 2 criteria to assess its performance. We have the parallel coordinates here, and there is embedded an optimization algorithm within that picture. So as that experiment runs, you can express preference to certain properties, depending on your criteria or criteria in particular property trend that you identified. And then this change is imposed to the optimization algorithm on the fly in real time. And then, of course, that makes the optimization study more focused, and we accelerate the process to come to the answer that we are looking for. We'll try the same with more complex scenarios. So again, we'll go to the airfoil. If you notice, there are 3 elements here, different type of aerodynamic study, and so on. And the next thing goes, okay, the reason I'm not demonstrating that live is because that is a framework that runs on a virtual machine. That's a bit heavy, and that causes now new kind of difficulties. So then we developed a web-based interactive framework. So then you use just your credentials, you log in somewhere, and then you do that as everything happens in the background, and what you see at the front end is something like that. So you can visualize your flow, you can make your analysis here, you have your scatter plots, and so on. That was also controlled with a workflow manager that is kept in this particular example. So then the next question that arises is, okay, we've done this. Now, this is not the first time to try to study and design this particular blade. We've done this in the past, of course, okay? And then often we did this doing physical experiments. So that means there is a lot of information available, historic information, and then it will be useful somehow to make use of that. So if we expand this cycle on this aspect, then we might have dynamic data drivers. This could be either from a database from experiments, or actually during flight test, or even real operation. Rolls-Royce, they monitor every engine that flies. You can imagine how much information they gather. Actually, they don't know what to do with this information, with this data. So if we infuse this information to the cycle, then of course you can appreciate like we can achieve even more benefits. So that was one part of my talk. I don't know how I'm doing with time.
I would say you still have another 15 or so.
Okay.
10 to 15 minutes.
Excellent. Yeah, because in my title I said visual analytics, which you've seen some, to directly support value assessment, but you haven't seen any value assessment. You've seen assessment of optimization data, but then what is value? It's not dollars. Value is the perceived value of a product from the customer's perspective. For example, an aircraft, how much valuable is to you? It's not like how much money Airbus does from that, but it is to you, the value of an aircraft is how cheap the air ticket is, how much legroom you have when you sit down, how many devices you can use during operation, during flight, whether you can make phone calls and that sort of things. So this is the value of an aircraft to the customer. So we would like to take this into account when we develop new aircraft or new engines even. Now how to do that? There's a particular way to do that. And then I'll go through relatively quickly, but I believe I will pass the message on that. So in order to do that, we need to come one level up where these kind of products are just concepts or architectures, as they call them. Now, when you have an architectural description of a product as an aircraft, then surely you don't have dimensions. You just have description of components. You have a fuselage, you have cabin, you have wings, and that sort of thing. Now, how to model that? I'll take you to a more kind of familiar product or object many of you might have used to cut the grass. So if you pick up the components here without necessarily having geometrical definition of them, then this is a matrix definition. We call this design structure matrix. So we have here the list of those components that describe this architecture in both columns and rows, and then we put a dot when two components connect. So then you have here a representation of these particular components. Okay? Now, once you do that, then you can start playing with this matrix. You can rearrange the components to identify connectivities for clusters. If we rearrange this, you can identify these for clusters. And how these relate? Well, they relate in this fashion along here. So then you can develop modules of your architecture. And that helps you to study them more efficiently, of course. Even more, I mentioned in the very beginning, if you remember, I work in the change management, engineering change, that is. What that means is, by change here, we model either a failure or change of specifications. So if you have a particular component, you want to change it for whatever reason, you would like to see how this will affect other components further down. What is the rippling effect? When you start poking one aspect of your system, how that propagates. And then we can do that. We'll provide a bit more information in here in terms of the likelihood this change will happen, and then when it happens, what is the impact? And then you take a picture like that. When you propagate this change, you take a picture of the risk. Now, that is another aspect of information that we can gather at this level when you don't have geometrical description, for example. Now, we would like to synthesize this high-level information with a more detailed information that you've seen in the previous part of my talk. And this is what we call here value assessment, when you try to synthesize all of this together. Now, the questions we try to address here, if we try to develop an aircraft, okay, what architecture to choose? Which of those? All of them are aircraft. Now, if you take the stakeholders in terms of Rolls-Royce, Airbus, GKN, then they have different expectations from that product. Airbus guy might say, I would like to have a quick and flexible response to market demands. That's common language. What does it mean to the engineering domain expert? The guy who designs aerodynamics of the wing, for example. This communication is hugely important. So I have another block diagram to describe this process, which I don't stay much here, but then I can show you this through an example. So say we wanted to design this particular component now of the engine, and we would like to find and assess architectural components meeting these new engine conditions. Now there's a tendency to change the engines. They call them higher bypass ratio. Although you might see them a little bigger, in reality inside they are smaller. Now this particular component carries structural loads because it links the engine to the wing. Here, remember, we have very hot flow, so they carry thermal loads as well, and aerodynamics, because you need to produce a thrust, and you like to have the maximum thrust possible. So that component, although small relative to the rest of the engine, it's really, really critical. So here is how this approach actually establishes communication between different domain experts. So then we'll go through the method. So again, I don't stay too much, but I hope I manage to pass the message. So we start from here, then we build these design structure matrices. We have them here, we can simulate them, and we take some sort of information like this that we can visualize in the parallel coordinates environment, if you're familiar by now, I believe. Now, you might have noticed here, in the left-hand side of the graph, there's not much density of points, and in the right-hand side, there are a lot of points. The reason for that is, on the left-hand side, we keep this description, high-level description of the architecture. So you don't have many architectures, you don't have hundreds, you might have 6 or 7 different architectures to consider. But then each architecture, if you choose, and you define at the next stage a geometry, then you can produce thousands of different geometry combinations. And this is what happens there. So with that way, you can actually bridge the two worlds together. And that is the same pictures in more detail. Some other interesting features here, which I don't want to overload you. I would like to bridge to that picture, which visually explains exactly what I said. So we have this type of representation. You simulate this information, you keep it here, and then you link it with a more detailed geometrical, with a domain expert. So here are the architectures, the aircraft architects, and then here are the domain experts. And then they can work on the same environment. They can express preference here, the domain expert, that would reflect back to the architect, and vice versa. Okay, so that gives the communication together. Just in pictures, one example from this particular element. So we have one geometrical feature here, some thermal constraints, and then a number of assessment criteria. We use this value assessment methodology to develop this particular value criteria. So then what we do, similar kind of approach, of course, we bring up a scatter plot, we choose 2 of the critical quantities. One is the mass, of course you would like to have lightweight in an aircraft, and then we would like to maximize the minimum expected life of that component, so then we make this choice here. That was just a design of experiments, so it was not a particular optimization study. So then we apply here optimality criteria to down-select interesting solutions. As we do that, then you see the reflect here to the domain expert in terms of the lean angle, that is a geometrical characteristic, that then they can focus down there and then they can perform the expensive optimization studies in this regime of the design space, not to the whole thing that they initially considered. If we then continue and we impose additional limits to the constraints that we have, then that focused even more. And then that is the useful thing, how we can communicate and how visualization is really important to establish that. And then perhaps I can show you this quick video with another example. So I hope it will start. Yeah. It's only a couple of minutes and I will start explaining in a second. That was an earlier version of the same software that I used earlier. So that's again another example. Now that is the result of aerostructural thermal analysis. So 3 different domains coming together. And then again, we pick up criteria of different domains, and we apply Pareto optimality criteria. We try to minimize both fuel consumption and the weight of that. So we do this selection. We see how that will reflect to the picture. But because here we had 3 domains, we had another set of criteria to consider. So I will bring in a second another scatter plot. And then we choose again these different criteria. That will be the weight against the minimum, against the range in this case. So we try to maximize range and minimize weight. So I apply again Pareto optimality criteria here. And now I will end up with the intersection of these 2 selections. Okay? So that is another way to use actually visual analytics for that. And then as you do this, here I'm showing like, okay, I have 2 different selections, and then the intersection of that is shown in the parallel coordinates plot. And then again, that will give the intent to the domain expert to continue and perform his studies. What else we did after that was to play with the constraints, because we have here 2 particular constraints, and then start making more strict this constraint. I noticed like the weight actually was affected, which was one of the criteria. So that raises the question, the constraint comes from a different domain actually. That raises the question, what will happen if I actually show the scatter plot between these 2 properties. And then you can tell there is some sort of a negative correlation. And that correlation was not known to the expert actually. So when we found that, we were really quite excited actually. And that was not the case for the other constraint that came from the same domain, you see. So we can identify this type of relationships between. And to complete my picture, if I wanted to expand, of course, we have these now value creation strategies that we can also impose interactively into this computation design cycle. We use a lot of computations to do that. And I would like to close with the message that parallel coordinates is more fun when performed with friends. This is Alfred Inselberg, that was in one of the visualization conferences. I think it was in Paris a few years ago. So thank you very much.
I can't believe I didn't get a photo.
Next time, we'll do that both. Yeah. So, any questions are very welcome, or comments, criticisms, anything. Yes, please.
Thanks very much for a very interesting talk. We're trying to use some of the similar techniques with my PhD students, so we're very interested. One of the things that is very important in visualization is the end user from different fields. The acceptance of the tool might be different. So I've worked mostly with engineers, and where they're happy to use your tools, or where there's some resistance.
Yeah, I mean, when you work with big companies as Airbus, then they learn how to do certain things over a number of years. So this massive company carries a lot of momentum. So if you imagine you try to steer this momentum, you need to put a lot of effort. Yeah. So we're working towards that, and we try to introduce these kind of tools to them. So they are exposed. But then the moment, even when you try to introduce new tools to their process, these tools are more kind of academic tools. So they come with a number of bugs and all of that. We are all familiar with this. But getting there. So there is some resistance. At the same time, there is acceptance because we came up with really important findings for them. Yeah? I didn't go through greater detail here because it wasn't the point of my talk. And perhaps another reason might be confidentiality issues. Right. But then surely they appreciate the approach and they try to work their heads around that. And they try to find ways how to infuse this new type of technology into their work. So there's a number of research projects that we work with them to try to do that. Yeah. So we have commercial software like MSC software. They have a platform, they facilitate synthesizing various tools together. So with them we work to synthesize our tool within the platform, which is a ready product that goes into the company. And in this way we approach this kind of achievement in a way. Yeah. I don't know if I answer your question, but
I have a question. How
Yes.
about the academic engineers? How do they react to that?
exactly, yeah, that's another challenge, indeed. So again, working on that. So I work with parallel coordinates since 2006, and only over the last 2 or 3 years, I acknowledge some acceptance of my proposals to my seniors.
Interesting.
Yeah, they can see some mileage in that approach, they say. But I would like to think like I'm ahead of them over about 10 years or so.
Yeah.
So let's see. The other thing that I forgot to mention, and now I remember, is we try, of course, to utilize new type of technologies as well, which might help us actually to bring more people closer to this type of analysis, as it is a virtual reality or augmented reality. But then again, visualizing this type of scientific information to virtual reality environment is not established yet. So we're working on that also. I didn't share anything yet because we have a paper currently under review. So I didn't want to breach this kind of requirement like it should be all novel when you submit the paper. So in the next talk, I will be able to share some more on that as well. Yeah.
Just the same sort of, had less success than you in persuading people with parallel coordinates, although we had the Israeli people up to do the geometry shape descriptions from them, which are really good. One thing I think was missing about 10 years ago was resolution.
Yep.
because I was trying to explain things on 10, 15 years ago on much smaller screens. That when I was able to get two high resolution screens and sort things out recently, I think that's helped.
Great, excellent point. Yeah, exactly. Because it's not only the resolution, it's also the size. I believe they go hand in hand. The size of screens that are available. So during these projects, we organize workshops, and then we'll go to their facilities. And they have virtual reality rooms and all of that, but it's like playrooms for them. This type of technology is not integrated into their process. So they have these huge, like 90 inches screens, just standing there and then, right. So then, what I show you here on this small screen and projector, when I put it into there, even to my eyes makes huge difference, and even to them. So that was an attractive point, to come and talk a bit more about this. And then again, they come with more questions, so always I try to teach you and then, prove you wrong or something like that. But discussion is happening. So hopefully, they appreciate this even more. What else I forgot to show here is, within this particular environment, because to do visual analytics, you like to have some sort of computational mechanism supporting the visualization. So then we have embedded machine learning techniques. So once you upload data into there, you start doing your analysis, there are gaps in the data. So if you build a surrogate model, say a kriging or something like that, then you can use it and then see what will happen in this gap region of your data. Just perform what if experiments and so on. And then although the prediction might not be accurate, at least it might give you something to appreciate, and then you take it on board and you go to study it in more detail in a computational environment. Yeah? And then I could demonstrate that, but it's not that important at this stage. But we're working to that direction. So we integrate more and more kind of algorithmic support to the visualization to accommodate this kind of environment and discussion between domain experts.
Kind of interesting the difference in scale between the kind of problems we face in academia versus the ones that industry would face. So I wonder how many sort of objectives or constraints do you actually sort of tend to see in this production?
Yeah. Mm-hmm. I mean, in one of the examples that I show you here, we only had one geometrical input, and we had about 8 constraints coming from different domains. And we had 4 different criteria to consider, again, coming from different domains. So it's kind of the other way around. It's very small input and many outputs. Now, the reason for that in that particular example was because you need to synthesize different domains together. That means their input, they should share a common input, in order to be able to synthesize them together. It's a representative example of what they do, actually. Although optimization is in their daily routine, the studies that they do, they are not huge at the moment. They're quite specialized in particular. They try. The other thing I should say, perhaps, is like you use optimization not necessarily to solve your problem, but actually to understand the problem. And that's really important. Okay. So it doesn't, when it is a real-world application, it doesn't mean like there are 100 parameters or 200 parameters, something like that. Of course, there are examples like this also. Okay?
Does that come down to the speed of the sort of validation in terms of the fact you've got to do a whole finite element simulation?
Look, I mean, the finite element simulation, you don't take into account how many elements you have in your domain of simulation to consider them as parameters. Okay, these are the parameters of your model, but then the parameters of the problem might be different. Okay, and usually there it's much smaller. It depends on the application, really. Okay, the other problem that they have, because now with the computational power, one thing, and then the optimization intelligence, the other thing, you can actually tackle huge problems. But then the problem is, okay, what to do now with all of this information? How can you assess what is better than the other? Even if you have many objectives, say 6, 7, or 8 objectives, the Pareto optimality is not great criteria to consider, because with 8 objectives, pretty much all of your candidates, they will belong to this trade-off, 8-dimensional trade-off. Yeah. Okay. That is another aspect, which is very interesting for the optimization community. Yeah.
What was that software that you were using?
That is CAM. We call it CAM. It's a Cambridge Advanced Modeler. So we developed it in-house. So that allows to represent these DSMs, and you do the change propagation analysis. And now we've introduced a visualization, and that is for free. You can download it from our website.
So anybody can download it.
Yep.
What do we search for?
If you search, well, if you do Engineering Design Center, there's a category tools. You go to the tools, Cambridge Advanced Modeler, you click and you go to another website, maybe another page perhaps, and then you download from there. Now you might not get this latest version,
Yeah.
but you get any version. You need to fill in a form simply to keep record of the users, and then actually you get updates when we release the next release. If you do that, you fire an email to me and then I can send you the latest version. So then you can play with that.
Cool.
Last version 2014.
Okay.
Just what you download.
Sure. Yeah, I mean, we plan to release with all of those features, well, we said that last year, but then getting there, so in the next few months, I suppose, we'll manage to do that.
Any sort of hints on the ordering of the axes? Any heuristics there?
Right, I mean, that is an issue, true. Now, if you noticed in my approach, on the data, on the type of data that we try to analyze, I always approach them from the criteria point of view. So typically you have 2, 3, 4, 5 maybe criteria, so it's quite specific. So then in the 26 or 45 input parameters, if the arrangements were different, it wouldn't make any difference to me. Okay, the shape of the pattern will be different, but it will be the same pattern. Okay, so I can see the same problem there, but then in this type of data that we deal with, we don't have this issue, which are a bit like I think. Otherwise, I know there are other tools that will do this parallel coordinates matrix. So they put all the possible combinations of axes to rearrange, and then you choose the one that appeals to you. Yeah.
Any other questions or comments? I saved a silly question for last. Did you show any of this? I should know the answer to this, but I don't. Did you show any of this to anybody in engineering at Swansea University? Is anybody?
No.
Okay.
In one of the last events that we met, the DIPART down in Filton, one of your colleagues with a supercar was around.
Yeah, Ben Evans.
Exactly.
Yes.
But then he had to go because he was
left
super busy.
immediately, Yeah.
Being, developing
Yeah.
supercars.
Yeah.
So my talk was the day after. So we missed the chance
Yeah.
by a day. But I was very interested, to communicate with you.
It is.
I know.
Yeah.
Because I also know that you do great work on visualizing flow data. And synthesizing the two would be really something.
Yes, it's true. It's true. I'm trying to remember if we ever put those things together, like flow simulation and parallel coordinates here at Swansea, and I don't recall doing that so far.
There you go.
We did try an experiment with tree maps together with flow simulation,
Alright.
which I absolutely loved. I loved it, but we didn't. I don't think we tried parallel coordinates. Oh no! I take it back. Zhen Bin Peng combined the two.
Okay.
I take it back, and we have experimented. And who was involved? A gentleman by the name of Nick Croft. I don't know if you've ever heard of Nick Croft, Ian Masters, and Rami Maki.
Right.
So they were involved. So they have, I can't remember what they said about it, but they are definitely co-authors on that on that project. But it was a little while ago now. But it's a good one. I like it.
Yeah.
I like it.
Yeah. And I think there is a future in introducing VR into that. Because VR traditionally is used to represent 3D geometries, not quite simple data. So much tempted to show you one snapshot of that attempt actually that we did. But then it does make a difference because we did an experiment bringing in novice users both in terms of data analysis and parallel coordinates. And they could actually identify patterns that you see here just with 20 minutes training on how to use the device and actually the environment. We use the gamepad for the navigation into virtual reality. So if we synthesize the nice visualizations of the flow of the products, that would be
that would be a good combination.
Yeah.
So
good. Things to think and do in the future,
Yes.
That's a good thing.
Any other questions or comments?
I'll be around for the whole duration, so if anything happens later on, feel free to ask me. Or even later, send me an email.
Thank you. So now we're going to attempt a group photo on the staircase of the Digital Technium, which is just outside. Any of the locals will know where that is, but you can literally see it right over there. And the sun is shining, so we should like race over there.
In the meantime, is the door room locked?
I wouldn't recommend leaving a laptop here. I would, well, the doors are not going to be locked.
Okay.
Yeah.